Today is January 30th, 2012, and this is AP Statistics at Berkeley High School. This is our conclusion of the Chapter 9 topics, Section 9.3, Tests about a Population Mean. Big picture one more time. We started with this general idea of what do we mean by significance tests? What does it mean to create these null and alternative hypotheses? What does it mean to set an alpha value? What does it mean to have a type 1 error? What does it mean to have a type 2 error? Big ideas in Section 1. In Section 2, we applied it to tests having to do with proportions, things that are related to categorical variables, yes or no questions. And then today we're going to look at what does it look like when we do things having to do with population means as compared to population proportions. We will review the ideas of checking the conditions for a test of population mean. We will conduct a one sample t-test about a population mean. We will, Sophia, right here. We will talk about the relationship of a confidence interval of a population mean to a two-tailed test of significance. And then lastly, we'll talk about the special thing called significance tested for paired data, or data that's coming from a matched paired experimental design. So let's get started. In the last section, we used the relationship of the distribution of sample proportions to do significance testing for questions that involve categorical variables. We used the Z table, we used Z values to find out how improbable a particular outcome was. Well, as we switch to a test of population mean, we are going to have to say, is it appropriate to use a Z-test? Well, it was appropriate to use a Z-test for the distribution of population proportion because that distribution was normally distributed with a known standard deviation, that square root P1 minus P over N thingy. Okay? But when we switch over to a test of population mean, we have to say, well, is the distribution of sample means normally distributed? Well, it is, and we can use the Z value, but only when we know what the sigma thing is, the population standard deviation. Do we know that? Hardly ever. So the Z-test, or the Z-distribution, or the Z-table is an inappropriate tool for that. So what are we going to use? Well, we're going to go back to the T-distribution, the one that we introduced last chapter. Okay? And we have one page of that, of your probability tables, which is specific to the T-distribution. Remember, the T-distribution depends on degrees of freedom. And in this case, the degrees of freedom for the T-distribution is related to the sample size. There's n minus 1 degrees of freedom. So, let's get started and do a problem. These questions are actually becoming less and less contrived and more like what's really going on when people use statistics in the real world. So, a company claims that their new AAA batteries last longer than their normal AAA batteries. Based on years of experience, it knows that the old batteries lasted 30 hours. Maybe I can put this in the context of you're working for Consumer Reports. And Consumer Reports rates items all the time and test things all the time. You decide for your report that you're going to test 15 new batteries, and you found that those 15 new batteries lasted indeed 33.9 hours. That does seem larger than the 30 hours. But the question is that difference real? Is it significant? Or is it just a lucky sample?
You better keep that door like
You know what? I got a better idea.
we're gonna get distracted like at least 2 more times. I feel like.
Let me use this one. Shut the door behind you, Luce. Thanks.
Are you about to do that like every day?
Depends. If there's only 2/3 of the class here when I'm starting, yeah, I'm going to start doing this every day because all this hardness is unacceptable.
It was like 1:30.
I'm sorry? Because that means people will be able to understand how angry I am as I greet them at the door.
Yeah, it's understandable. I was just wondering if you was gonna do it over there. I didn't have a problem.
I'm going to continue on with this problem, if you don't mind. Okay, so they took a sample of 15 batteries. They got 33.9 hours. The question is that 33.9 hours really evidence that these new batteries are longer, or maybe we just got a lucky sample that came out that way. We know that things have variation. Not every battery lasts exactly the same. So is it a real difference, or is it just a lucky sample? How are we going to make that judgment? Well, we've got a procedure that we can follow. It's the four-step process. Let's talk about what it looks like in this particular case. As with the one that you did for population proportion, I need to start out saying, what am I investigating? How am I measuring it? What's my null and alternative hypotheses? And what's my alpha value? So what's our population here? All AAA batteries?
Yeah.
No.
Yep.
No. No. First of all, our sample is 15.
The company.
Okay, wait. The company's batteries getting closer. The new AAA batteries. Not all AAA batteries. This company's, but not just this company's, but the new ones. We want to test whether the new ones last longer. So, new AAA batteries. Okay? What is the parameter, or what is it about these AAA about these batteries that we're investigating? The mean lifespan? Okay, so we're going to measure the mean lifespan. Notice that the word parameter is followed in this case by the word mean. In our previous section, the parameter was followed by the word proportion. So something that's how we're measuring it. And right now we're measuring things we're summarizing these ideas using proportions and mean. Mean life span. All right? Okay, how about a null hypothesis and how about a alternative hypothesis? P is incorrect here. P is great when the parameters are proportion, mu, and not x bar, right? Because we're really interested in what's going on at the population level. We're trying to make this conjecture about all of these batteries, not just the 15 that we're investigating. Is mu what? Equals 30. Remember, that represents an assumption of no difference. I'm going to assume that these batteries aren't any different than the old ones, and then I'm going to see if I get this low probability, which is going to be able to get rid of that claim and replace it with what we're really trying to prove, which is mu is greater than 30. That there is a difference, that these do last longer. alpha value is our last thing on this area.
0.05.
Why 0.5?
Because I don't think.
Because if they don't give it to you, assume 0.05. It's the most typical alpha value. So there we go. Step 1 is done. So far, so good? Great. Let's go on to step 2. Conditions. Oh, by the way, if you look at your scaffolding sheet, one of the things that's listed there is the names of the tests that we're doing. When we're looking at means, I think I gave you 4 options. One is the z-test. Second one is the z-interval. The third one is the t-test. And the fourth one is the t-interval. Which one is this? Well, we're doing a significance test, so it's not the word interval. And it's going to be the t-test. And what's going to lead you to that conclusion, Jacob?
Do these data give convincing evidence?
Well, the word doesn't give it convincing evidence, leads us to the conclusion that it is a test as compared to an interval. So that is a phrase that's very important, and it leads us to the conclusion that we're doing a test of significance. That therefore we're using the H0, the HA, and that's an important phrase. Now, between the z-test and the t-test, where's the decision point? What is it that we look at in this narrative that's going to tell us? I'm going to summarize.
Wait, it should be Z because we have standard deviation. Is it?
There's your summary of how you make that decision.
So it is Z.
If you're given sigma, you should carry out a z-test. If you're not given sigma, you should carry out a t-test. Katya, take your idea forward. Tell me what you're thinking.
Well, we have a standard deviation of 9.8, so it should be Z because we have standard deviation.
I'm going to circle that. All right? So there's a standard deviation. My question is it sigma, though? There's sigma, which is the standard deviation of a population, and there's S, which is the standard deviation of a sample.
Yeah, that's S.
Okay? So this is really S. And if that's S, do we know what sigma is?
No.
No. So no sigma, we're going to have to do a T. I would rather use a Z. I'd rather have sigma. But again, it's really, really odd that we ever know a population level number in this kind of work. Right? So we don't have sigma, we're going to do T. So the name of the test that we're going to do is called a t-test. And there are 3 conditions associated with the t-test. The first 2, we've gone over so many times, I'm going to gloss over it pretty quickly. Is the sample unbiased? You answer that question by asking, is the sample random? Is it random? Yep, there's our random. It's SRS. So we're good. Is it independent?
Depends.
It depends. I believe it depends on whether the population is greater than 10 times our sample size, or in this case, 10 times 15. Do we think it's reasonable that the population of the new batteries produced by this company is more than 150?
Yeah.
If it isn't, then this is a very, very small company, and AAA batteries is not where it's at for them. I mean, I usually buy the AAA batteries in packs of 100 myself, so it'd be really unusual. So I'd say, yeah, I think we've got convincing evidence that we're okay there. Let's talk about the last one. The last one is normal. Do we recall the special normal conditions that are associated with the t-test? They're like 3 layers thick, kind of like a cake or parfait or an onion. parfaits. Parfaits are better.
You never had like a hole in it, right? So
Moving on. All right, so there's 3 levels of conditions for this t-test. One is the sample size is really small, less than 15. Then the sample's got to be like really normal. Hey, but our sample size is exactly 15. We get to go to the second layer. Second layer is if it's between 15, greater than or equal to 15, but less than 30, then we ask the question, is it about normal? Is there evidence of strong skewness or outliers? If there's strong skewness or outliers, we can't use this test. At least we can't use it safely. But if there's no evidence of skewness or outliers, we're good. Well, let me show you what this sample looks like. Okay, in this middle chart, they have a dot plot of the sample, they have a box plot of the sample, and they have something that we haven't talked about in a long time called the normal probability plot of that sample. So if you look at the dot plot, what do you think? Skewness? I'm not seeing much. Outliers? Possibly. You know what we do if it's like we have questionable. I mean, I assume that you're looking at this one, Kyle, right there.
yeah, that can.
Okay, so said, I don't know. Let's run the box and whisker plot. Let's run the box plot that shows us whether there's outliers or not. Here it is. You know what they say? It's not an outlier.
But it looks good.
It looks a little skewed, so maybe if we're worried about skewness, maybe what we should do is do the normal probability plot, which is built into your calculator as well. Remember, the interpretation of the normal probability plot is if the dots are linear, then the distribution is approximately normal. Would you say that those dots line up well on that line?
Yeah.
Pretty close. Pretty close. The book is going to say that we should feel okay about using the t-test in this instance. Now, because this is subjective, not the outlier part. We have a really hard and fast rule for outliers. But since the interpretation of this is subjective, I'm going to give you leeway. If you see something that you're concerned about, you may point it out, and if you act appropriately based on that reaction, I'm fine with it. It's subjective. All right? But the idea is you either declare this to be not strongly skewed and no outliers, and then we can move on, or you say, I see outliers. Proceed with caution. I see strong skewness. Proceed with caution. All right. So, going back to our, to our chart, we're going to say no outliers or strong skewness. Give me a check mark there. Okay, are we ready to proceed to part 3? The calculation phase? Well, just like we talked about in the previous section, you got to give me at least 2 things in this phase. You got to give me a test statistic. In 9.2, that test statistic was a Z. In 9.3, that test statistic, for the most part, is going to be a T. What is the formula for the T test statistic? It is X bar minus mu divided by the square root of, divided by S divided by the square root of N. And in this case, let's plug and chug the values that we know. Do we know what X bar is? I believe it is 33.9. The average length of life from that sample of 15. Do we know what mu is? Yeah, mu is what we said in our H0. In fact, sometimes that mu is referred to as mu naught. Do we know what S is? 9.8. And do we know what the square root of, well, square root of n and n is 15. And we also have to declare here how many degrees of freedom are we working with? 14 degrees of freedom. So there we go. Calculators, can you? 1.54. Can anyone confirm that?
Yep.
You got it too?
I put it up. I can clear my.
Try it again. Come on. I want to have this calculation because of its fractions, because it's a fraction within a fraction, because it's got a square root. It's difficult. I want to make sure that you can handle getting this in properly.
Yeah, it is.
1.54. All right. Now, the test statistic was only one part of that calculation phase. The other part is we have to convert that test statistic into a p-value, into a probability. All right? The probability that t, and then I steal the inequality arrow from there, is greater than 1.54. By the way, I might put next to t a little subscript 14 for 14 degrees of freedom. And now we got a problem. In the previous section, we went to the z table and we were able to get a probability. Now we're going to have to go to the t table, and we're going to have to use the t table in a way different than we used it previously. Let me switch over to the t table on my screen. All right. So when the last time we used the t table, we pretty much only used it using that bottom row to calculate how wide we have to make our confidence intervals in order to get either 95 or 99% confidence. But the t-table also works in the other direction, meaning we have something up here on the top row, and this is why make sure you get your probability tables out now. I'll wait for you to get them out. You may share one with someone who's sitting near you. I don't think you have one. You need the T. You have it? T table. So look at the top of your T table. Has everyone got theirs out now? It says tail probability P. Now what does that mean? Well, let's take a number that we know really, really well from the t-table, 1.96. We have said in the past that 1.96 meant that in a t-distribution with an infinite sample size, centered at 0, that if we go to 1.96 and we go down to negative 1.96, that we capture the middle 95% of that, of all those things, typically X bars. Now what that means is that there's 5% that's unaccounted for. Where's that other 5%? In the tails. So how much is in this tail right here? 2.5%, which I will write as 0.025. And what you do, if you started that column at where it says 95%, and if you go all the way up to the top, you can see that 2.5% right there. So the top of the row, very first list of numbers are what's referred to as the upper tail probabilities. By the way, there's also 2.5% down there because it's symmetric. So here's what we're going to do now. We're going to take this number that we just got from running the statistics. I believe it was 1.54. And we're going to see if we can translate that into a probability using that top row of numbers now. Get rid of my drawing. First of all, I only want to look at the the line with 14 degrees of freedom. Right? Now, it is extremely unlikely that the number that we just calculated for the t-value is going to be in that line. Most likely what's going to happen is it's going to fall in a gap. So if I look and go down this line, 1.54 falls between those two numbers, 1.345 and 1.761. Now, I'm not going to be able to get an exact probability out of this table, but what I can say is that the probability that we're looking at is between 10% and 5%. Is that enough to be able to make a decision in our step 4 of the process? The answer is yeah, it is. We don't know that we don't have to know that it's exactly 7% or 8% or 8.3%. All we need to know is it bigger than alpha?
Yeah.
Whatever it is, it's going to be bigger than alpha because it falls in that gap. So now we're ready to go back to our 4-step process and write in what we know. That the probability that t is greater than 1.54 is larger than 0.05. Or you want to be more specific, is between 0.05 and 0.10. Either saying this directly or saying it's between those two numbers, as long as we get an idea of how is this going to relate to our alpha value. And now we're ready to finish the process. We have a p-value, we have an approximation of a p-value. We may now say, because the p-value is bigger bigger than 0.05, sorry, what's the mantra? Bigger than our alpha value of 0.05, we fail to reject. Ch9. And now we've got to finish it off with the context statement. Remember, you got to memorize this by test time on Thursday anyway, so you might as well try to do it right now.
There is insufficient evidence to suggest the true insufficient lifespan.
Insufficient evidence.
There's insufficient. Took me a long time to learn how to spell insufficient. Insufficient evidence to suggest
Does that have to be exactly that?
there's no reason for variation on this. You want to nail it? You do it exactly like this. The true mean, except I would write it neater if I were you. The true mean life span of new AAA batteries.
Well, if you said like, there's insufficient evidence to suggest the lifespan.
Nope, nope, because we're looking, one, how are we measuring that lifespan? We're measuring it by using the mean. And when we're talking about the mean, there's a sample mean that looks bigger than 30. We're not interested in a sample mean being better than 30. We're looking for evidence that all of these AAA batteries will have a mean life of bigger than 30. We're asking for a very, very big thing, and that's why we're going to go exactly with this wording. Is greater than 30 hours. Okay. And that's a four-step process with this. Four-step process with this kind of data. Okay. That's the hard one. Are you ready for the shortcut? Does anyone know what I'm going to do next?
Probably about to put it in the calculator.
I'm going to show you how to do step 3 on the calculator. All right. One of the downfalls on the quiz from Friday was a lot of you guys were able to put this in the calculator and get a number out. Many of you then had no idea that once you calculated the test statistic, that the test statistic ended up right there. That was one of the downfalls from using your calculator on the quiz on Friday. You know what the other downfall was? The other downfall was the interpretation that 8.5 blah 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 times 10 to the negative fourth. Actually, it doesn't show up that way on the calculator, does it? I think it says 9.5 something e negative 4. That this means 0.000 3 zeros, because there's 4 there, 8.5. Many people wrote down that the p-value was 8.5. That a probability number is 8.5. Hey, there's an 850% chance of rain today. Doesn't make any sense.
Could be the last one.
No. Probabilities are numbers between 0 and 1. So, great tool this calculator is, but if you don't know how to read the numbers on it, we got a problem. But let's switch over to the calculator version of this and see what it looks like. Let me clear this off. Let me go to stats. Let's go to tests, and let's see if we can find the thing that we need. T-test. Option number 2. Okay? Now, here's something we haven't seen before. T-test asks us, do we have the raw data, meaning do we have how many hours each individual battery lasted, or do we have statistics that summarize our data? We have statistics. So let's switch over to statistics mode. Hit enter. So now it's going to ask us, what's mu naught? Or in other words, what was the value associated with mu equals in the null hypothesis? 30 in this case. Okay, what was x bar? 33.9. What was s sub x? What's the standard deviation? 9.8. And how big was our sample size? 15. And lastly, is it mu, for the alternate hypothesis, is it mu is not equal to 30, mu is less than 30, or mu is greater than 30? Greater than. Now we can say calculate, and you can see that the t-value comes out exactly the same. And please note that using the calculator, we don't get a range of values that p falls into. We get the p-value, 0.07. Does our interpretation in step 4 change? No. The interpretation in step 4 is exactly the same. This p-value is still too high in order to reject H0. We would fail to reject H0. Did we get all that down? Am I okay with you doing this on the test? Absolutely. Do I mean to also say at the same time that you don't need to be able to read this table? No, I do not say that. You need to know how to get values out of this table as well. All right? One last thing I want to throw out there. How might they have run this test differently, or how might they run this experiment differently to increase the probability that they reject H0? Change the sample size. What I'm talking about is increasing the power, that the power is indeed the probability they actually reject H0 properly. And maybe I can do that by increasing the sample size. I'm going to do this test again. I'm going to pretend instead of having 15 in their sample, how many do they have in their sample? 30. Great. And what happens if the only thing that changes is the sample size? Interpret, please.
There is sufficient evidence.
There's no sufficient evidence to reject H0. Or in the mantra that we have in there, because this p-value of 0.01 is less than the alpha value of 0.05, we reject H0. There's sufficient evidence to suggest, or we, what do I have written down in the mantra? We believe that the true mean lifespan of these AAA batteries is indeed greater than 30. Sample size matters. And that's why to increase the power, we can increase the sample size. What was the other way that we can increase power? Change alpha. So if the alpha value, instead of being 0.05, was 0.1, we could have accepted it. We could have rejected H0 in that case too. But isn't there a danger increasing alpha? What's the danger of increasing alpha? Abby says type 1 error. What does she mean, Paul? We end up rejecting H0 when indeed there was no change. We make an error. How often do we make a type 1 error when the alpha value is 0.1? What? 10% of the time. Are we willing to make 10% errors? No. At least I'm not willing to. But, I'm not an executive for a battery company either, so who knows what they're up to. All right. So that is finishing off that entire problem. Now let me sketch ahead. There's not much more here. Here's their write-up of what we just did. Here's the formula that we use for T. You can use the calculator, but you need to be able to read that table as well. Remember, T changes with degrees of freedom, and not every degree of freedom is listed on that table. And if we fall in a gap in degrees of freedom, what should we do? We go with a lower degree of freedom. For example, there's no 55 on your table. You can't do degrees of freedom equals 55. So go to 50 if you're stuck with the table. Guess what? If you use your calculator, you don't have that problem. If you go to the calculator, they have no problem with 55 degrees of freedom. Any questions about T tables, degrees of freedom? Conditions for using the T? Remember, small sample sizes, less than 15. You have to have samples that are normal. 15 to 30. No strong skewness, no outliers. Greater than 30? Jazz hands. Anything goes. Strong skewness, we don't care. Outliers, we don't care. Because the central limit theorem takes over by that point. All right. Okay, and this is them just doing what we already did. Okay, we did all of that. Okay, and we just said all that too. Oh, here's something that didn't get said. Sometimes we get negative t values. Sometimes we get negative t values. So for example, our alternate hypothesis might be in some circumstances mu is less than 20. And then when we go over to step 3, we might get that t is equal to negative 1.75 with, let's say, 10 degrees of freedom. Let's talk about what goes on in step 3 after we find that p-value. I want you to get in the habit. I demand that you get in the habit that you have to write your probability statement. P. P what? Probability that our test statistic, then I go over here, and I steal the direction of that inequality, right, is less than, oh, that's supposed to be a negative there. And now we got a problem. Our t-table doesn't have any negative values on it. Uh-oh, what are we going to do? Give up? Wah, wah. Nope. Try again.
Symmetry.
What's that?
Okay. Symmetry.
Symmetry. What about symmetry, Paul?
Yeah.
Symmetry. There's some symmetry. That's a different kind of symmetry. Conrad.
The probability that t is less than negative 1.75 is the same as it is greater than 0.67.
That's right. So if we want to look it up on the table, we just treat it like there's a positive value and a greater than, and we'll get the same number. Is that clear? Okay. So let's do that right now. Let's test your t-table reading skills. I got 10 degrees of freedom, and I've got a p-value. Sorry, I've got a t-value of negative 1.75, and I want to know what range of probabilities that particular statement falls in. What do you got? Nope. How about I pull up on my big screen? There we go. Whoa. Oh. So 10 degrees of freedom. 10 degrees of freedom. And I'm looking for what? 175. That falls in that range. Okay. So we're going to say that that negative probability that t is less than negative 1.75 has a probability of between 5 and 10%. Whoa. Where'd it go? I think Excel just crashed. Okay. All right. Now, I got one more question. And again, consulting your t-table. And this is one of those unusual things. Stop bothering her.
That's my stuff.
Stop bothering her, yo. I'm trying to learn. Trying to spike game and
You know, we got that recorded. And that would be admissible evidence in a court of law.
I'll take care of her after class.
If anything happens to her, you are so...
She's like clean my whole house.
That is both like derogatory and like...
The worst, right?
I mean...
What is she supposed to do?
Oh.
I guess make me food too. I don't know how I missed that.
Oh, okay. We're moving. I'm going to put you back into the class now. All right. So, here's another situation that you're likely to encounter. Are you ready? What if the t-value wasn't 1.75? What if it was 17.5? How would you interpret that t-value? And let me see if Excel indeed crashed on me here. Nope, there it is. So here's Excel. Here I am with 10 degrees of freedom, and I'm looking for the gap where 17.5 is. the biggest number in that line for 10 degrees of freedom is associated with a upper tail probability of 0.0005. So what is 17.5 going to be? Very, very small. Essentially 0 is the right answer. Or if we want to be really conservative, we'd say whatever that probability is, it's less than 0.005. It's really small, which means it's likely to be good evidence to reject H0 no matter what the alpha value is. Really large t-values, like 17, are strong evidence against the H0 claim. Or if we're looking to be less than a t-value, because there's negative 17.5 again would be strong evidence against a H0 claim. Okay, we got one more variation of this to handle. Okay, one more variation of this to handle. What if the HA claim is not equal to? How does that change things? Well, last time we talked about this, we talked about the not equal sign leads us to say an absolute value around our test statistic in our probability statement. Right? We said that the not equal sign means it's a two-tailed test. If it's a two-tailed test, what does that mean? It means that we got the probabilities from both tails that we have to account for. But your t-table only has probabilities for the upper tail. So how are we going to square that circle?
Makes it worse.
If it's a two-tailed test, and the table only gives us that, but what we want is both sides of there, we got to double the probability. On a two-tailed test, let's say that t-value fell between 5% and 10%. We double both of those numbers. In a two-tailed test, we'd end up saying, translating from the table, the probability is really between 10 and 20%. We double both numbers. Of course, the easier way would be just to use a calculator. I'll give you exact answers. Go into the calculator. If you say your alternate hypothesis is a not equal to, it will double the probability for you. All right? But questions on the test are going to be worded in such a way that you can't use the calculator. So you got to be familiar with both ways. All right. I think I'm done with that slide. This is the discussion of the negatives. We've already had this discussion. What's the probability that t is less than negative 3.17 with how many degrees of freedom?
36.
It doesn't say. Let's go with 30. Okay, so 36 degrees of freedom. So wait, if it's 36 degrees of freedom and we're using the table, what line do we have to go to? 30. Okay. And then, even though this is negative, we're going to change it into a positive value and say, oh, we fall in that gap, don't we? Which means we are in a probability that's between 0.0025 and 0.01. All right? And the calculator, again, will give us exact values if we choose that. All right. Okay, I think we got all those points down. And there's our summary of our three different tailed tests: greater than, less than, and not equal to. Do we have any questions about this?
Under 17%.
I don't know. Let's see what else is in these slides. You ready? All right. Okay. Oh, By the way, we can only do this if what? If we meet our conditions. There are samples that are either large enough or they're normal enough. And remember that population's got to be much bigger than our sample size. All right. So, let's do another example. But in this example, I give you raw data. Would you please get out your calculator? Would you please enter these 15 values into your calculator? We're going to do this one all the way through together with raw data. That means you need to get a calculator out, everybody. I did. No, I don't want to block your view of the data just to see me enter the data in. Jacob, do you need a calculator? Can I get one for you? I'll turn it on for you. Can you get the data in, please? We'll wait. No, we will. Stop. Okay, while Jacob is finishing entering the data, let's start attacking this with the four-step process. Population. No. It's not about dissolved oxygen. That's the thing. We're at Whoa. Okay. Just to let you know, you have a four-step process for your quiz tomorrow. We've gone through one. You may go through another one before you take your quiz. Don't forget to get your stuff out of your hanging folders. Those people who did not take the quiz on Friday or otherwise hold me a quiz, I need to see you.